Hey students, all right, try another solution here. Someone was asking about another rotational piece. So this one says the propeller of a World War II fighter plane is 2.3 meters in diameter. Now be careful right there, diameter. So half of that is the radius. And that's an easy mistake to make, is just forgetting, okay, now how big is the radius? Because a lot of our things are listed in radius. And yet they gave us here diameter. So that's always a one to keep in mind. So A, it says, what is the angular velocity in radians per second if it is spinning at 1,200 revolutions per minute? Now, I would say this is kind of a pushback to Chapter 1 and converting units. I talked about how to convert units, and especially because you might run across, and this might be the time now, that you're going to see some units that you've never used before. And so we just need a logical strategy in order to solve this. And that's where my thinking was to say, you won't change this number if you multiplied by 1. And if you do a clever one, you then will convert the units. So if I ultimately want this in radians per second, let's get rid of the minutes. So I'm going to put minutes in the top and seconds in the bottom. That's how then minutes would cancel off, and I'd get seconds in the bottom. More on radians and revolutions in a second. But of course, to make it work, you got to make sure that the number in the numerator and the number in the denominator are the same when you include the units, so that you are only multiplying by a 1 and you're not actually changing the number. And so all you do is change the units. Now, don't get me wrong, when you change the units, you got to change the number for it still to be equal. It'd be like saying 2 feet or 24 inches. So the number of the units change together such that the whole thing doesn't change. And that's what's happening here, is what I have so far would change this into so many revolutions per second. And so the other part of this is a conversion from revolutions to radians. So I'll put revolutions in the bottom and radians in the top. That way, the revolutions would cancel off. And so now I just have to make sure my numbers match so that this whole thing's equal to a 1. And that way you take your original number, multiply by 1, and you really have the same number. Perhaps different units, and perhaps a number that goes differently with those units, but still has the same meaning. And so here I would say 1 revolution is 2 pi radians, because that's a whole circle around. 1 revolution is a full circle. Full circle is 2 pi radians. So looking at the units, I would have now just converted it into radians per second. So now I'm ready to get my calculator. So here's 1,200. Looks like right here I would multiply by 1 and divide by 60. And here I would multiply by 2 pi and divide by 1. Well, divide by 1, that's a waste of calculator space, but hit enter there, and I'm looking at 125, and I'll just go 0.7 radians per second for A. Now moving on to B here, what is the linear speed of the tip at the tip of the angular velocity if this plane is stationary on the tarmac? So in other words, we only have to worry about the rotation, not the forward motion of an airplane. So this was the mathematical connection between linear speed and rotational speed. So let me take the radius, and again, just remind you that they gave me a 2.3 for the diameter. So I'll take the 2.3 and cut it in half. That'll be the radius. And I just worked out what the speed would be in radians per second. And so grabbing my calculator, 2.3 divided by 2 here, times the last answer that's in my calculator, gives me a speed of about 144.5. And this is a good time to mention units again. I did that in an earlier problem, but again, radians is a pseudo unit. That is, the angle is defined as an arc length over a radius. These are each measured in meters. So technically, radian, or a angle in radians, doesn't have any units. We only put radians in there because it just feels better to say the speed is 120, the angular speed is 125.7 radians per second, instead of just saying 125.7 per second. Just sounds funny. And so that's a little bit of clarification. But the reality is that is just a clarification, and over here it actually makes things worse. It doesn't clarify them. If I were to say the linear speed is 144.5 meter radians per second, that just doesn't help. In fact, it hurts. So I'll drop the radians with the justification of they're not real units. They're clarification stuff. So this would be meters per second. And so that would be the linear speed. C then, really getting kind of the heart into this chapter, is what is the centripetal acceleration of the prop's tip under these conditions, and calculated in meters per second squared, and also in multiples of g. So let's just go with the centripetal acceleration, which we can write as either v squared over r, or we can write it as r omega squared. We got both the omega and the v. Maybe I'll just use the v, 144.5 meters per second, and I'll square that. And then I'll divide it by the radius, which is 2.3, divided by 2. Maybe I'll start with the 2.3 and divide it by 2 and get 1.15. So that's the radius. So in the numerator, if I go up here and grab that speed and then square it and then divide by that radius, I would get a centripetal acceleration of 18,160. And it might be nice to look at the units. I'd get meters squared in the top and another meters in the bottom. That leaves just 1 meter in the top and then a second squared. And luckily enough, or coincidentally enough, or unit analysis, is this would be the speed or the acceleration in meters per second squared. So that's good. Now, the other half of this question said divide it by g. And I guess they didn't explicitly say divide it, but they say convert into multiples of g. In other words, how many times bigger is it than g? So that's why I'm choosing to divide it by g. And so this is about 1,853 times bigger. Well, there's no units, but sometimes we like to refer to this so we can have some kind of feel or connection, is that the g-forces of this thing spinning around, if, let's say, you were on that propeller, or maybe a little ant was hanging on to that propeller, their weight, their force, in order to hang on, would be 1,853 times greater than their weight. And so if it was a human, and that human weighs, say, 170 pounds, this would be the equivalent of somebody weighing 315,000 pounds. And you can imagine if you weighed that much, you would just get, you know, smashed into the earth. You would just be this blob of glue. And so that's what would happen on the propeller. Although you wouldn't shrink up into a blob here, you would shoot off the end. You just couldn't hold on. There's no way you could use your legs or your arms and all of them combined to hold on to something when you weigh 1,800 times more than your normal weight. Just not feasible, not possible. So nothing's going to hang on here. I mean, it's just going to go flying off. It's even hard to get dirt to stick. I mean, dirt would have to go shooting off here. So you indirectly clean your propeller just by the high motion of it. Okay, hope that one helped too.